Okay, so I'm starting the recording now. So for the lecture part of today, there's going to be a seminar part afterwards, as I've just discussed, which is going to be course feedback, and that's not going to be recorded. For the lecture part that's going to be recorded, we're going to look at a main example of some problem that's interesting to compute, and see how this particular example sheds quite a bit of light on various aspects of computational complexity. And then we'll end with a summary of essentially the material we've covered in the lectures, so the complexity classes we've covered in the lectures, just to sort of fit everything in the, not everything in the course, but to put the course essentially into a single picture, the material we've covered in the course. The example I'm going to mainly talk about is the permanent of matrix, which is an example that two people on the course already looked at in more detail. Neither of them are here now, but looked at in more detail for the. You didn't know, did you? Yes. Oh, sorry, sorry, you didn't do it. Right, okay. So sorry, I'm getting you good. It was a very good presentation, and you're going to see some of what you covered in your presentation covered again in today's lecture. So that part will be easy, but we're going to do other things too. So we're going to look at the permanent of a matrix, and I'm just going to begin by reminding you what it is, and it's something similar to the determinant of a matrix that we all know. So let's look at the determinant versus the permanent of n times a matrix. And these are both things that it's useful to compute for different reasons. So the determinant is the famous thing we have, and there's the Leibniz formula for it, which says to compute the determinant of a matrix, you sum over Sn is the symmetric group on n generators. Sorry, no, the symmetric group on n elements. Sorry, which means the group of all permutations on n elements. So we're summing over all permutations on n elements. We take the sign of the permutation. I hope you all know what it is. Basically, it's odd if you have to do an odd number of swaps to get the permutation, and even if you need to do an even number of swaps. That's well defined. And then you product over all numbers from 1 to n, and you consider a, I, sigma I. So that's the famous formula for the determinant, and the permanent is the same formula but without the sign. So again, we sum over all permutations, and we product over all elements of the matrix, so over all indices from 1 to n, and we again go a, I, sigma I. And both are interesting mathematical concepts. The determinant is very important in linear algebra and in geometry. Whereas the permanent is important in combinatorics. And essentially, the determinant gives you a handle on computing volumes, the determinant of an n by n matrix is the hypervolume that a unit hypercube gets mapped to under the linear transformation given by the n by n matrix. The permanent is important for counting problems. And the simplest illustration of this that I'm going to stick with, the simplest illustration is the following statement, which was also mentioned in your presentation, and maybe in the first lecture. The permanent, I'm sorry, I'm repeating a little bit of what was in the first lecture, but that doesn't matter really, because I want to remind you of it, and also this is like the lecture material, essentially completing the circle. But now we've got the complexity theoretic tools to understand what we're talking about, so to be able to understand how difficult problems are. So the permanent of an n by n 0, 1 matrix, you can view it as counting the number of perfect matchings in a bipartite graph. I don't know if you're familiar with all these, or two of you certainly are, but everybody is familiar with all these terms. A bipartite graph and the kind of bipartite graph that we're interested in perfect matches. A bipartite graph is one where the vertices are divided into two collections of vertices, so that there's a partition of the vertices. You might call them the left vertices and the right vertices. In general, those sets might have different cardinality, but in order to talk about perfect matchings, they need to have the same cardinality. So here we're interested in a bipartite graph in which you've got the same number of vertices on the left as the same number as you have on the right. There's a graph with the left set of vertices, the right set of vertices, and all the edges are between vertices on the left and vertices on the right. So the vertex on the left might connect to some vertices on the right, like that one might connect there, maybe this one will connect there. I mean, there's many ways, many possible bipartite graphs you could have, but this is one. So here we've got two n vertices, n on the left and n on the right. And a bipartite graph on two n vertices can be represented by an n by n matrix. So if we considered its usual adjacency matrix, that would be a 2n by 2n matrix. But there's a special bipartite adjacency matrix that's appropriate for bipartite graphs. I'll call it the bipartite adjacency matrix. And the point is, every row will correspond to a vertex on the left, and every column will correspond to a vertex on the right. So we're going to have 3 rows and 3 columns. We've got 1, 2, 3, and 1, 2, 3. And so here we've got, does vertex 1 on the left connect with vertex 1 on the right, which it does. We have a 1 here. Does vertex 1 on the left connect with vertex 2 on the right, which it does, so put a 1 here. Does vertex 1 on the left connect with vertex 3 on the right? It doesn't. So we have a 0 here. Does vertex 2 on the left connect with vertex 1 on the right? No. So 0, and then we can just fill it in. And this particular graph has, I think, this adjacency matrix. So vertex 3 connects to 1 and 3. So vertex 3 connects to 1 and 3. And then a perfect matching is a set of n edges such that every vertex appears in exactly one edge. Or equivalently, the set of n edges forms a bijection from the left vertices to the right vertices. The n edges bijection between left vertices and right vertices. So, how many perfect matchings are there in this graph? Let's see. Somebody can answer on Zoom if they want to as well. I don't know. Hopefully you can see. Any guesses? Is there a perfect matching? Is there any perfect matching to begin with? Anyone want to say yes or no? So it would be a collection, in this case it would be a collection of 3 edges, such that every vertex appears in exactly one of the edges. Can we find 3 edges such that every vertex appears in one of the edges?
1, 2, 1, 2, 2.
Right, so the horizontal lines provide one perfect matching.
And then the 1, 2.
And then the slanted lines provide another perfect matching. Indeed. Are there any other perfect matchings? Yeah, so in this case there aren't. And the reason is, as soon as you pick any one of the lines, it forces the others. So for example, if we pick this line to be in the perfect matching, in this particular case, this isn't usually the case, perfect matches, but in this particular case, if we pick this line for the perfect matching, then we can't have this line in. So because there needs to be a line with this, it needs to be this one. And once we've got these 2 diagonals, then we're forced to take the other one. And similar to the other. As soon as we pick one edge from the perfect matching, in this case, it determines all the others. And we could have also got the same number by computing the permanent of this matrix. So this would be an inefficient way of computing the permanent, but we can see that it corresponds to perfect matchings, because essentially a perfect matching is a bijection between vertices such that every parent in the bijection is an edge of the graph. And here we're summing over bijections. Here we're summing over bijections between left and right vertices, such that the product of the edges is well, and then we're summing the product of the edges, but all the numbers are 1 or 0. So this product will either be 0 or 1, and it's only going to be 1 in the case that all these values are 1. And that's saying that this permutation is a perfect matching. And we sum over all permutations, those permutations that are perfect matches. So that's why the determinant is counted the number of perfect matches. So in this case, the number NO dot means the number of perfect matchings equals what it always equals the permanent of the matrix. So this matrix is A, and that in this case is 2. Example above. So how did, I mean, if we wanted to calculate this permanent, then, well, we could use this formula, but it's very inefficient to compute this formula. So can we do better than using this formula? So let's think about that. And that's the interesting computational question. Can we do better than using just the formula that sums over all permutations, of which there are factorial many permutations? That's a nasty number, worse than exponential. So how might we be able to get a handle on how to compute the permanent? And this is something that was mentioned in your presentation. The permanent has a nice property, as does the determinant. So we're going to look at some properties in which they're quite similar to each other. So the determinant and the permanent are both what's called downward self-reducible. And that means computing the value can be reduced efficiently to computing smaller instances of the value. So efficiently reducible. So one can give a formal definition using Oracle computers, but I'm not going to do that. So efficiently reducible to smaller instances of the same problem. So, for example, computing a determinant of some matrix. So let's consider 3 by 3. So if we consider a matrix like 3, 1, 4, 1, 5, 9, 2, 6, 5. Computing the determinant of that, or one algorithm we have for computing the determinant is to go along the top row, pick out each value. I mean, we all know this, I hope, from linear algebra. Pick out the top value and multiply it by the determinant of the remaining square matrix if you knock out the rest of the row and the column from that value. So we pick out 3, then we multiply 3 by the determinant of 5, 9, 6, 5. So it's 3 times the determinant of 5, 9, 6, 5. And we go to here, we do 1 times the determinant of, well, we knock out the row and column, so 1, 9, 2, 5. But for the second entry, this is where the sign comes in for the determinant. For the second entry, we subtract. So it's minus 1 times the determinant of 1 times the determinant of 1, 9, 2, 5. And we add the determinant, and the top number is 4, so 4 times the determinant of the square matrix, we knock out the row and column and take the 4, so 1, 5, 2, 6. So plus 4 times the determinant of 1, 5, 2, 6. And there's a very similar formula for the permanent. So the permanent of the same matrix. And of course, it's irrelevant what the numbers are here. So basically, I'm going to replace these with variables, and this is a formula for reducing the permanent of an arbitrary matrix. So here we have 3 times the permanent now. of the, so we're reducing it to the permanent of a 3 by 3 matrix to the permanent of a 2 by 2 matrix. And unsurprisingly, given the difference between the determinant formula and permanent formula, the only difference is that we add all the numbers, so there's no subtraction here. So we add 1 times the determinant of 1925, and we add 4 times the determinant of 1526. So if you wanted to state rigorously what's going on here, if you wanted to be so rigorously what it means to be downward self-reducible, well, these are particular examples, but rigorously what we're doing is we can compute the determinant of an n, the determinant of a permanent of an n by n matrix. So I'll say the size n version of a problem. In polynomial time, given an oracle, but we don't time the oracle just gives us an answer, given an oracle for smaller instances of a problem. So given an oracle that can, it's not very rigorous, but anyway, just saying how oracle machines are used in the mathematical definition of downward self-reducibility. So here, if we've got an oracle that will give us the determinant of a 2 by 2 matrix, then this little formula is essentially a polynomial time algorithm that will give us back the determinant of a 3 by 3 matrix. So that can solve the polynomial time given an oracle that can solve instances of the problem. Of size less than n. The thing is, this is not and does not give us an efficient algorithm, because we might use the oracle more than once. So it gives us a recursive algorithm for computing. This gives us a recursive algorithm for computing the quantity. If we've got downward self-reducibility, we reduce for a size n problem, we make a recursive call, and the recursive call is on smaller sizes, but we might be making many recursive calls. So this gives us a recursive algorithm. Solving size n problems without an oracle. But it's not polynomial time because we're making many calls. At each level, we make many calls. We've got a tree that branches. It need not even be exponential time, because the width of branching might depend on n, as it does in this case. And so here as n gets larger, the branching, the number of times we make the recursive call is always n, where n is the size of the matrix. So in fact, when you work that out, here we don't have just exponential branching, we have exponential time, we have factorial time, which is a little bit worse than exponential time. Okay, so this doesn't give us an efficient algorithm, but at least it's a nice bit of structure that various problems have. And this is an important aspect of various computational problems when a problem is reducible to smaller instances of the same problem. Okay, so we have two different algorithms now for computing the determinant of the permanent. One is just to calculate the formula at the top, the formula that we started with, the Leibniz formula and its version of the permanent. Now we have the version based, the recursive algorithm based on downward self-reducibility, which is also not efficient, has a similar complexity. As you know from exercise classes and perhaps from other courses, like algorithms courses, in the case of the determinant, there is an efficient algorithm. So the determinant does have an efficient algorithm. Whereby an efficient algorithm, for the sake of this course, we mean that that belongs to the appropriate complexity class. The appropriate complexity class, well, we saw language decision problems of the determinant earlier in the course. But now that we've had it last week, really the appropriate complexity class, the determinant is a function, and it's a function that's computable in polynomial time. There's a question, what are we forming the determinant over? So sometimes we compute the determinants of a matrix valued in the rationals. Sometimes we compute it matrix valued in a finite field. Actually, the definition of the determinant makes sense for any ring, but the good properties of the determinant actually rely on having a field rather than a ring. And also, I think the efficient computability. I mean, we're normally interested in working in fields. Anyway, for either the rationals or for a finite field, as long as the finite field is efficiently computable, the determinant is itself computable in polynomial time, even basically in n cubed time, in fact, in something a bit better than n cubed time. And as you did, I think we did this in the exercise class, this essentially follows, so this is for any field in which we can efficiently compute the operations, and this basically follows the algorithm. It's basically by Gaussian elimination. Basically, the steps of Gaussian elimination act on the determinant in a way that it can, that it can be easily recovered. The determinant of the additional matrix can be easily recovered from the determinant of the result of the Gaussian elimination. If you do a Gaussian elimination, you end up with one of these matrices that's sort of in some sort of triangular form. But if the determinant is going to be non-zero, it will actually be an proper upper triangular matrix, and the determinant of that is just the product of the, so all the left-hand corner will be zeros, and the determinant of that is just the product of the diagonal entries. But you did that in exercise classes, so I won't go into that. There's a little niggle in this, a little fiddly point, which is to what extent you use division in this. And if you use division, then division's a bit of a complicated operation, and it's a little bit hard to see what's going on. In fact, Gaussian elimination can be formulated without using division, so that's one way of getting around that problem. Or you only need one division at the very end or something. I'm not going to talk about that more. So basically, determinant is efficient. This contrasts with the situation for the permanent. This is very surprising given the formal similarity in how they're defined in the first place. So I don't know, when we were giving this example, that we could either look at the number of perfect matchings here, which we can see what's going on, or we could have tried to compute the determinant of this matrix, which isn't too hard because, sorry, the permanent of this matrix, which isn't too hard because we can just use the random self-reducibility and Baronia to 3 by 3 matrix, so it's not actually that much work to do. But in general, given the matrix, how can we compute the permanent? Well, turns out it's very difficult, and there's a nice theorem that you mentioned in your presentation on the random, on the interactive proof of permanent. There's a nice theorem, which is, in contrast, the theorem by Leslie Valiant, who's contributed an enormous amount to the subject of computational complexity. Valiant's theorem, 1979, and that is that permanent is sharp P complete. So it's a sharp P problem. It's equivalent to computing the number of witnesses of an NP problem. Even that's not terribly hard to prove, but it takes a little bit of work. But more than that, any sharp P problem can be reduced in the sense of last week, using an oracle to the permanent. So if we have an oracle for the permanent, then we can efficiently solve any sharp P problem. And this is proved by reducing sharp SAT to the permanent. And in fact, it's not just permanent, but it's even permanent of a 0-1 matrix. Sharp P. Now it's easy to see that it belongs to sharp P because we're counting the numbers of perfect matching, the number of perfect matchings in the bipartite graph. So that can be easily formulated as counting the number of certificates for a polynomial decidable property, namely whether the certificate gives you a perfect matching in a bipartite graph. And so even computing the permanent of a 0-1 matrix like we had is as difficult as any sharp P problem, including the problem of counting the number of satisfying assignments to a Boolean formula. So that's a really stunning result. And at the start of the course, my ambition was in this last lecture to actually prove this, but it's a very long and complicated proof. And yeah, I think we've done enough long and complicated proofs. But one main one was which we didn't do in full detail, but I mean, the main these complicated proofs about interactive proofs. So I'm not going to give you the proof of this, but I just want to say the proof is complex and ingenious. It has lots of stages to it. Anyway, it's a really important result, and consequence of this, just to remind you of this, and then we'll have the break. consequence of this is that it's very unlikely that we can efficiently compute the permanent in the sense of it belonging to FP. That is polynomial. There's a polynomial time algorithm for computing a function. So if the permanent belongs to FP, then we get our usual bad consequence that we expect not to be true, that P equals NP. So this is a way of saying it is unlikely that we can compute the permanent in polynomial time. And the reason for this is the permanent is sharp P complete, therefore sharp sat, computing the number of satisfying assignments for a Boolean formula is reducible to an oracle for permanent. But if we had the permanent computable in functional polynomial time, then we don't need an oracle. Instead of calling the oracle, we just apply our functional polynomial algorithm. And so therefore if the permanent was computable in functional in polynomial time, then we could compute the number of satisfying assignments of a Boolean formula in polynomial time. So we could decide satisfiability, because if that's not zero, we could decide that in polynomial time, so P would be equal to NP. So we don't believe we can compute the permanent efficiently. And it's now 9 o'clock, so we're going to have a break until 9:15. Let me pause the video. When I find it. Okay, so we've seen the consequence of Valiant's remarkable theorem that computing the permanent of the matrix is sharp P complete is as hard as computing the number of satisfying assignments for a propositional formula, is that if we can efficiently compute the permanent, then we can then P equals NP. So it's unlikely that we can efficiently compute the permanent. But in fact, it's even more unlikely than this makes out. So it turns out that the consequences of being able to compute the permanent in polynomial time are much stronger than just P being equal to NP. So in fact, there's a stronger corollary. The bottom line is the permanent is basic. Computing the permanent is harder than, we believe, is significantly harder than just solving satisfiability. So solving satisfiability is enough to get P equals NP to do that efficiently. But in fact, if the permanent is efficiently computable in polynomial time, then P is not equal to just NP, but in fact P equals the full polynomial hierarchy that you've looked at in exercise classes, a little bit looked at an analogous hierarchy in the homework. So this is the polynomial hierarchy. The whole of the polynomial hierarchy collapses to P. Mind you, that follows from this. Yeah. So actually, that's not a strong corollary. Yeah, I need to correct my notes. What is stronger is the following fact, which doesn't follow from that. Yeah, sorry. That was I noticed that. And even more, what's even stronger shows that computing the permanent is stronger than solving satisfiability is the following, which is Toda's theorem. Which says that the whole polynomial time hierarchy is contained in the class of polynomial time algorithms with an oracle for Schottky problems. This equals, by Schottky completeness, is those polynomial time problems with an oracle for solving them permanent of a 0-1 matrix. So if we have an algorithm for computing the permanent of a 0-1 matrix, then there's a polynomial time decision procedure that uses that algorithm for any problem in the polynomial time hierarchy. Okay. So this is saying that being able to compute the permanent is very powerful. So this doesn't hold for an oracle for SAT. If we say polynomial time in an oracle for SAT, we can't compute the whole polynomial time hierarchy by polynomial time algorithms with an oracle that just gives us a yes/no answer for a satisfiability problem. But we can compute any language in the polynomial time hierarchy with a polynomial time algorithm with an oracle that says compute me the permanent of a 0-1 matrix. That shows that the permanent of a 0-1 matrix is a very, very powerful thing to be able to compute. And again, this is another theorem with an ingenious and proof that I don't want to make this lecture very technical. Ingenious proof and tricky proof. Really, again, it involves several different stages to it. Even outline the proof would take a lot of time. I only really want to do one thing technically this lecture, and this is the next thing I'm going to do. So this is going to be the little technical content of the lecture, and this is actually something that you also did in your presentation. So it's not going to be new to the two people who gave the presentation on the permanent. So the moral of what we've got so far is it's hard to compute the permanent correctly and exactly on all inputs. So it's then natural to vary the question a bit and ask, well, can we at least compute the permanent if we relax some of the conditions? So we said compute exactly. I mean, we're looking so far at computing it exactly using a deterministic algorithm on all inputs. There are various things we could relax there: the deterministic algorithm, the computing it exactly, and the on all inputs. So let's look at the on all inputs first. So what if we changed computing the permanent on all inputs to just having an efficient algorithm that worked on most inputs? Works on most inputs. I'm immediately going to hide that because I want to use the top board. So that just says, what if we had no algorithm that works on most inputs? That's no. That's also like this. Seems likely to work. This is Lipton's theorem. So this is the one thing I want to prove in the lecture. And it says permanent is randomly self-reducible. It's like a random self-reducible. So what does this mean? It means if we can compute the permanent correctly on random instances, then we can compute it correct. Then we can, with some probability of error, compute it correctly on, with an arbitrarily low probability of error, we can compute it correctly on all instances. So the version of the theorem I'm going to prove is the one in the textbook, and it can actually be improved. So the one in the textbook is, suppose we have an oracle for the permanent that computes correctly, if we give it an n by n matrix on a 1 minus 1 over 3n fraction of n by n matrices. So and we're going to assume we're computing the permanent over a finite field. You can always assume you're computing the permanent over a finite field, because even if you're computing in the integers, you can pick a large number that bounds the maximum possible value of the permanent, and find a prime bigger than, find a prime around the size of that number, and then take the appropriate finite field. So over a finite field F. I'm going to put in the assumption in the textbook, which is where the size of the field F must be greater than 3n. I'm actually at a bit of a loss to see where this is used in the proof. So particularly you two that have looked at this, if you know where this is used in the proof after we've done the proof, I'd be interested to know. Maybe we'll save it till the question time. So suppose we have this, an algorithm that works on a large fraction, 1 minus 1 over 3n is quite a small, quite a number quite close to 1, so it works on a rather large fraction of the inputs. But given this, then we can actually compute the permanent on all inputs with a probability of error. But we can make the probability of error arbitrarily small. So then we can compute on all inputs all n by n matrices by a probabilistic algorithm. So we're relaxing the deterministic and the computing correctly on all inputs. We're looking at probabilistic algorithm that might make some mistakes on a few inputs. But, sorry, yeah, we're going to give a probabilistic algorithm that has a small probability of making mistakes. That probability is for all, on any input, it's going to have that probability of making a mistake. The probabilistic algorithm, the prop algorithm, alg dot, that for any input matrix, returns the correct result we're going to do the usual thing of bounding the probability of correctness by a number strictly greater than a half. So the probability of correctness is going to be greater than or equal to some constant. Well, actually, it's not a constant in this case, but so the probability that we get out of the proof is 2/3 greater than or equal to the probability of correctness of the permanent computed on any input is going to be greater than or equal to 2/3 minus 1 over n. Minus 1 over 3n, sorry. It's not a constant, but as soon as n gets, well, as soon as n is greater than or equal to 2, this is already greater than or equal to whatever, something like 4/7 or something like that. Well, when n is strictly greater than 2. The point is, once we've got this, we can do the usual thing of running the algorithm many times to reduce the probability of making an error in an efficient way to anything we want to. And in fact, a more difficult proof, this fraction, we're assuming that the algorithm that we take as our oracle works on almost all, just we only make a mistake on 1 divided by 3n inputs. But this fraction 1 minus 1 over 3n, so with much more work, the fraction can be improved to any constant c strictly greater than a half. So in fact, I'm not going to prove this, but in fact, the same statement holds for any constant fraction. So as long as you have a majority of matrices, the original algorithm works on the majority of matrices, then it's possible to get a probabilistic algorithm that has high probability of being correct that works on all inputs, all input matrices. So this is the one technical thing I want to do in today's lecture. I don't want to have it devoid, today's lecture completely devoid of maths, and so apologies to the two of you that did this in your student presentation. Right, so what do we want to do? So we want an algorithm that's going to take an arbitrary input matrix and is going to find, for that arbitrary matrix, is going to find its permanent in a way that is very likely to be correct. Well, very likely means probability at least 2/3 minus 1 over 3n. That's just a little technical. Basically, the probability of being correct is around 2/3. So that's A be the input matrix. And the probabilistic algorithm is going to do the following. So, A, B, B input matrix is the algorithm. So I'm going to give the algorithm. So what we do is we choose a random matrix, a random n by n matrix over the field. So that R, so it's an n by n matrix over the field. Be a random matrix chosen uniformly. So for each of the n by n entries of R, we uniformly choose one of the number of size of the field of F elements of the field, of which there are at least 3 n many, though I'm not sure why that's important, as I said. And we now define a polynomial B of x, which is the input matrix A plus x times R. So scalar multiple. And this is a polynomial. Sorry, we now define, sorry, let's not say this is a polynomial. We now define this. So for any value of the field, it gives us a matrix, an n by n matrix back as a result. The n by n matrix is A plus X times of R. And we observe two things about this. So firstly, if we calculate the perm, we consider the formula that calculates the perm of the matrix. We can consider this, if you like, as a matrix, all of whose entries are linear polynomials. So the top, the 1, 1 entry is A11 plus X times R11. And if we consider the formula for computing the permanent of this, the sum over all permutations of the product of all the appropriate entries, or because we're summing the product of n things, and each n thing contains at most one x in it, we get a polynomial back in one variable, x. So it's a univariate polynomial. It's a one variable polynomial, univariate polynomial. And because we're summing a product of n things each time, the maximum number of the maximum exponent of an x that can appear is n. So it's of degree n. At most n. That's equal to n. That's equal to n. And secondly, if we take any non-zero entry of the field, so any A not equal to 0 in F, if we compute B of A, it's a random matrix in the space of all random matrices, in the space of all matrices over the field. Because we're adding a random matrix to some given constant. So if we put B equals 0, it's not a random matrix, it's the input matrix A. But if we add a random matrix to A, or any multiple of a random matrix to A, because it's a field, we again get a matrix that's uniformly distributed over the space of all matrices of the field. So it's a random matrix in R to the n times A. They're uniformly distributed. So now what we do is we choose, we don't need to do this randomly, we choose n distinct, n plus 1, distinct values, a1 up to a n plus 1, in the field that are different from 0. If it's the usual kind of Galois field generated by a prime number, we can simply take a1 up to an plus 1 to be 1, 2, 3, 4, all the way up to n plus 1. But if it's a different kind of field, we need to make sure that we don't have any values to 0. But the thing is, these don't need to be chosen randomly. They can be. We just need to have n plus 1 element. We just need to find n plus 1 elements of the field different from 0. And now we use the oracle to compute the value of the permit. To compute what the oracle tells us might be the permanent of B applied to A1 through to AN. So use the oracle on inputs BA1 to BAN plus 1. We're using the oracle n plus 1 times, and this produces n plus 1 values as results. N plus 1 results for P1 through to P n plus 1. The point is, because our oracle is only wrong on a small fraction of inputs, each of these is likely to be the permanent of the corresponding matrix with relatively high probability. Well, so for each I, Pi is the permanent of BAI with probability 1 minus whatever, at least 1 minus 1 over 3n. So let me write that down. So for each of these values AI, so for each I from 1 to n plus 1, Pi equals the permanent of BAI with probability greater than or equal to 1 minus 1 over 3n. Because we're computing the permanent of a random matrix, and our oracle only makes a mistake on at most 1 minus 1 over 3n. So our oracle is correct on this fraction of inputs. So it's going to return the correct answer on a random matrix with that probability. So then the probability that Pi equals the permanent of BAI for all I from 1 to n, square plus 1, sorry. Well, we've got in each case a probability of 1 divided by 3n of making a mistake. Now these values a1 through to an plus 1, sorry, these matrices ba1 through to ban plus 1, they're not independent of each other, they all lie on the straight line. They're all determined by the matrix. In the space of matrices, they're all a constant plus a linear plus, they're generated by this bx formula, which is giving us a straight line through the space of matrices. They're not independent of each other, but nonetheless, the probability of getting a mistake on each one of them is at most 1 over 1 over 3n. So we can at least bound the probability of getting an error. So the probability of getting an error on at least one of them is then n plus 1 times probability of an error on any one of them is 1 over 3n. So the probability of getting an error on at least one of n plus 1 of them is going to be at most n plus 1 times 1 over 3n. So even though they're not independent of each other, the worst we can get is that now. So this is greater than or equal to 1 minus n plus 1 over 3n. Each one might go wrong with probability 1 over 3n. Some of them might overlap on the probabilities of when they go wrong because they're not independent, but that just makes things better for us. So if they were all disjoint from each other, then the worst we could get was this. It's called the union bound. And this is 2/3 minus 1 over 3a, which is the value we wanted there. So now what the algorithm does, so we've got high probability, or this probability that all the values pi are the permanent of the respective matrices. And what we've got then is, we know that we've got a univariate polynomial of degree less than or equal to n for the permanent of b with over the variable x. So we've got n plus, with high probability, with this probability, we've got n plus 1 values of that polynomial of degree n. And if you have a polynomial of degree n and you've got n plus 1 values, then that then you can recover the whole polynomial. That's called interpolation. So we use interpolation, which I'm not going to tell you the algorithm for it, but it's a well-known thing one does with fields. So I use interpolation to find the unique polynomial degree n polynomial qx such that q a1 equals p1 and so on, q of a n plus 1 equals e n plus 1. And with probability greater than 2/3 minus 1 over 3n, these are the permanent of these p's are the permanent of the respective matrices. And then we simply return q of 0. And with high probability, qx is the polynomial that computes the permanent of b of x. So q of 0 equals the permanent of b of 0, which equals the permanent of a. And we're done. Okay, so that's random self-reducibility. So it indeed says what happens. It's indeed to do with computing the permanent on most inputs. And one way of looking at it is, if we take a stronger version of the theorem, not the one I proved, so if we can efficiently compute permanent on a fraction that's more than half of all inputs, then we can probabilistically compute it. So that's basically what the result says. So I don't know what I mean, two of you have met this before and thought about it in detail before. I mean, you might think that, great, this means that all we need to do is find an algorithm for the permanent that works on most inputs, and then we've now got a nice way of probabilistically computing computing the permanent. But actually, what it really means is actually a bad thing, because we know that it's hard to compute the permanent exactly, even probabilistically, because we would, in this case, get a BPP algorithm, and BPP is contained in the polynomial time hierarchy, and we've seen the polynomial time hierarchy is reducible to an oracle for the permanent. So the right way of taking this is that the complexity of computing the permanent on a majority fraction of the inputs is as bad as the complexity of computing the permanent on all inputs. And there's another way of looking at that. So in practice, one doesn't often deal with algorithms that you don't often think about algorithms that compute the correct answer on a fraction of the inputs. I mean, sometimes one does, but it's not a very common thing. But what is a more common thing is to look at algorithms that sometimes take a very long time, but in the majority of cases don't. So they're efficient, and in particular, I'm interested in algorithms that are often efficient on a typical or random input, but might behave badly on a few spurious, a few inputs that are not nice. So one's often then interested in algorithms that work efficiently, but not necessarily on all inputs. But what I want to point out is that that's essentially the same thing as looking at algorithms that compute correctly, as efficient algorithms that compute correctly on a fraction of the inputs. Because if you've got an algorithm that perhaps runs for a long time on some bad inputs, but on a typical input will compute correctly in reasonable time, you can turn that into an efficient algorithm that will make mistakes on some inputs by you run the algorithm for the amount of time you want to, and if it hasn't terminated, you then produce a random result. Okay. And then we're looking at what's called average case complexity. So what we get from this is that the average case complexity of the curve is no better than the worst case complexity. So we can't even hope to find an algorithm for the permanent that computes the correct answer and is efficient on an average input, but perhaps not on all inputs. So the note here. Oh. Okay, so it's bad news so far. So let me just end with some good news. So we can't compute the permanent exactly and efficiently. We can't compute it on the majority of inputs efficiently. We can't compute it using an efficient algorithm that works in the average case. Well, an algorithm with efficient expected time, but perhaps bad worst case time. None of these things we can do. But this is all to do with being able to compute it exactly, so getting the right result, at least on the majority of inputs in good time. All these examples have considered actually trying to get the exact permanent as the result. So a natural weaker question is, can we at least approximate the answer of the permanent? And here there is some good news, finally. And this is a theorem of Sinclair Oda 2001. So this is actually quite a famous theorem. And I was at the University of Edinburgh while Mark Jerram and Eric Igoda were working on this, and Eric was a friend of mine. It's a nice result for me to end the course with, which is, so I still want to do, in the next part, I want to do the synthesis of what we've learned in the course, which is not going to take very long. It's going to be a big picture, basically. But this is a positive result about computing the permanent, which is there exists a probabilistic algorithm that given and times that matrix with non-negative entries so we're now talking about real numbers or rationals, and the entries need to be non-negative, or integers, but natural numbers because they're non-negative, and an epsilon delta greater than 0. So we want to approximate the value of permanent. And the idea is for any epsilon saying how close we want the value to get, we're going to be able to compute an epsilon approximation to the permanent with high probability of success, where delta is giving us the probability of success. So the probability of the result of the algorithm differing from the permanent the matrix is A here, permanent of A. So here, taking absolute value, so how much it differs from the permanent over the permanent of A, which is positive, which is non-negative, because we've got a non-negative matrix. We want to get within a fraction of epsilon of the result. And the probability of that we make greater than or equal to 1 minus delta. And this can be done. The computation time is polynomial. In n, the size of the matrix, the log of 1 over delta. So this is just the usual thing, but to be able to approximate to within 1 over 2 to the power of n, we need polynomial in n iteration. We need polynomial in n time. That's what this logarithmic 1 over delta is. and polynomial also in how close we want to approximate, but not in the logarithm of 1 over epsilon, but in 1 over epsilon itself. Being able to compute polynomially the logarithm of 1 over epsilon would be too much to ask. Would basically allow us to compute the permanent exactly itself probabilistically. It enables us to do that. So a very nice positive result. As long as one wants an approximate answer, there is an efficient algorithm where if we take polynomial time to be efficient, so that's a beautiful result. The method of proving it is a really powerful method, which is we want to compute a permanent, so that can be reduced to a counting problem. And to count, one way of counting is to be able to sample uniformly from the space of all. So for example, if we wanted to count the number of perfect matchings, if we have a way of sampling uniformly from the space of all perfect matchings in the bipartite graph, so uniformly there's some number of perfect matchings, and we take a probabilistic sample of some perfect match of a random perfect matching with the uniform probability given the number of matchings. If we can sample uniformly from the perfect matchings, one can do statistics on what the perfect matchings look like and get an approximation for the number of perfect matchings. I mean, there's quite a lot of machinery goes into that, but it's a really beautiful and powerful idea. And then using that idea, they come up with what's called a Monte Carlo Markov chain that allows you to sample uniformly from the space of perfect matchings, or more generally something analogous for an arbitrary matrix with non-negative entries. So that's lovely, lovely mathematics in it, a lovely result, an efficient algorithm for approximating the permanent, if one takes efficient to mean polynomial time. But the bad news is the constants. So the polynomial, you have some polynomial that's bounding the time, there are constants in it. There are also constants in the coefficients of the polynomial. The constants hidden by the big O notation are large, and indeed so large as to make this approach infeasible. So they're infeasibly large. So actually, it's not usable in practice. Maybe in some special cases, some version of it does work in practice. I don't actually know. I mean, people wrote papers on this not working in practice. I don't really know what the current status is. And the lesser thing is, what about matrices with negative entries? But that's, I mean, being able to solve it for matrices with non-negative entries would be a very big step. So still people don't know how to compute the permanent efficiently. And with this, we get a cautionary tale that we shouldn't believe the propaganda, if we like, that efficient equals polynomial time in some sense. I mean, it turns out, it tends to be the case that if something, you have a polynomial time algorithm, the constants, for most natural problems, the constants tend to be small, and it turns out that that is much better than having non-polynomial time algorithms. And they are, in some sense, efficiently computable. But sometimes that's not always the case. So the abstraction and complexity theory of going to asymptotic complexity classes is not always a good model of efficiency. But nonetheless, you know, to be mathematical, if one wants to be mathematical and precise, I'm not sure what one can do that's better than taking asymptotic classes. Right, it's 4 minutes past. I want to start the next part with just a picture summarising a lot of the results of the course, and then we'll go into discussion about how the course went and feedback, and then there's a questionnaire for the people who are here in the classroom. So for the moment, I'm going to break, and we'll have a break just till 10:15 again. So it's 10 minutes break. Okay, so I just want to do for the last part a short stretch, maybe about 15 minutes, in which this is a synthesis of the course in some sense, but essentially what I'm going to do is I'm going to once again write down the diagram of complexity classes we've considered, although it'll be a bit larger now because we've considered a lot of complexity classes in the course, and while I'm doing so, put a little bit of perspective on it. Then once you've done that, I want a short discussion session with feedback on the course, and then for those of you in the classroom, I've got the course questionnaire for you to fill in if you wish to. Okay, and only the first part, only the synthesis part of the course is going to be on the recording. But the discussion part will be on Zoom as well. The feedback on the course will also be on Zoom. So I want to look, just to remind you, and sort of put in a picture what the main complexity classes we've considered, because in some sense, computational complexity is about charting out a territory of computational problems, and with each problem we want to classify it according to how difficult it is to compute. And the main tool we've got for doing that, and what we've been looking at in this course, is putting problems into complexity classes and then relating the complexity classes. So most of the course we've been looking at language complexity classes, in other words, the complexity classes associated with decision problems. And maybe I'll do this in the direction we started. So just to remind you how the course evolved. I want to leave enough space, so let's put P here. So we started off with polynomial time computability, and then introduced the idea of non-determinism. That's polynomial time computable in a deterministic Turing machine. Introduced the idea of non-determinism to give us non-deterministic polynomial time computability, the class NP, which gave us the famous P equals NP question, or is not equal to NP conjecture. In another direction, we have co-NP. The complement languages of NP problems. We then looked at space complexity, and we saw how this all fitted in. There are going to be inclusions here, but I'll put them in later because I want to put some more stuff in. So how all this fitted in polynomial space, which we considered both deterministic polynomial space and non-deterministic, and we saw that P space is equal to NP space, so non-determinism doesn't give us anything there. Polynomial space is contained with, we still have a time bound, and time bound for everything below. The time bound is exponential if we want to determinize it. So we want to determinize, if we want to look at how the time it takes to run polynomial space algorithm. And at some point during the exercise classes, you met something that contains NP and co-NP and fits in between P space, which is the polynomial time hierarchy. So I'm going to put that here. Polynomial time hierarchy. And we were looking at some extension of the polynomial time hierarchy in the homework. While we were looking at space complexity, polynomial space gives us a lot of power. Space complexity also gives us a nice way of restricting computational power. So we looked at logarithmic space and non-deterministic logarithmic space. And both of those classes of languages are contained in polynomial time. And a nice result about non-deterministic logarithmic space, which was proved in one of the student presentations, is that like polynomial space, it is closed under complementation. So co-non-deterministic logarithm, sorry, I don't know what I was saying. I meant non-deterministic logarithmic space, I'm not sure what I said, is closed under complementation, so co-non-deterministic logarithmic space is the same as non-deterministic logarithmic space. So there's an inclusion here. I haven't written it in because I'm going to put something between the polynomial hierarchy and polynomial space in a moment. After that, we looked at randomized computation and probabilistic complexity classes, and in particular, the most important class there is BPP, so the class of problems that are decidable probabilistically with a bounded probability of error, and that lives between polynomial time. The relationship with co-NP and NP is not known, but as you were told in the homework, it fits into the level 2 level of the polynomial hierarchy, so that lives in that. So between P and polynomial hierarchy, we've got various classes of interest, where this one, bounded polynomial, probabilistic polynomial time, is kind of the class that best corresponds to what is efficiently computable in practice. Modulo what I said about hidden constants and things earlier. I'll let me put this inclusion in, but I'm going to overwrite it. So after this, we looked at notions of ways of giving a verifier a proof firstly by interaction with an all-powerful prover that wants to convince a skeptical verifier that something is true. This gave us a class of interactive proofs, and we had the lecture just before Christmas in which I outlined the proof that interactive proofs are the same class as polynomial space decidable languages. And related to interactive proofs, we have the notion of zero knowledge proofs. These are included because a zero knowledge proof is a particular kind of interactive proof, which I didn't maybe emphasize it enough at the time. The two ways in which this restricts the interactive proof. Sorry, this is computational zero knowledge proof, the one I want to look at. The two ways this restricts interactive proofs, one important way, it was in the definition, but maybe I didn't emphasize this enough at the time, is that with interactive proofs, we assume that the prover has unlimited power. With computational zero knowledge proofs, the prover can be, it should be a probabilistic algorithm, maybe a polynomial time algorithm, maybe a probabilistic one. It has some additional information, which is the secret it's trying to hide. But with that information, it needs to behave in a computationally correct way. And that's useful because these proofs are actually things that are useful in practice. And it's important that they have efficient algorithms underlying them. So these are computational zero knowledge proofs, proofs that have a polynomial time probabilistic prover, as well as a polynomial time probabilistic verifier, and also have this property that the prover cannot leak the secret that they know to the verifier. And something else I didn't emphasize, so I outlined why 3 coloring has a computational zero knowledge proof. Because 3 coloring is NP complete, that actually means that every NP problem has a computational zero knowledge proof. So we also have this inclusion here. And lastly, to complete the picture, I want to put in a complexity class that we considered for the first time today. Maybe it was in the exercise class last week. I'm not sure. That is p to the hash p. So this is problems that have languages that have a polynomial time algorithm, where the polynomial time algorithm takes an oracle from a counting problem, for a counting problem. Without loss of generality, it could be finitely many counting problems without loss of generality. That counting problem could always be sapped, or it could always be determinant, because that's any sharply complete problem. And this is pretty much the picture. We've got the polynomial hierarchy, we've got all the various division of it into levels, but apart from that, this is basically the picture of the complexity classes that we considered in language complexity classes. Last week, we started moving to function classes. And here we've done much less. So basically, we've just looked at two. We've got FP, which is the analog of P, and we showed that that's contained in sharp P, and that's essentially what we looked at. Okay. And throughout the course, a very important idea has been to classify problems according to the complexity classes they lie in, and particularly showing that problems are as hard as any other problem in the complexity class. And so this was a major endeavor that we undertook. And this is the notion of looking at complete problems for complexity classes and understanding why they're complete and what the complete problems are. And not every complexity class has a sensible notion of complete problem. So the complete problems we looked at were particularly NP complete and the polynomial time reduction. It didn't make sense to look at complete problems in polynomial time itself, because every problem in polynomial time itself is automatically complete. It's not an interesting notion that if one considers polynomial time reduction. It's also interesting to consider complete problems for non-deterministic logarithmic space under deterministic logarithmic space reductions. It's interesting to consider complete problems for P space and also consider complete problems for NP space, but that's the same thing. And today we considered, and last week we considered complete problems for sharp P. So these are classes. Classes for which we consider complete problems. The amazing thing about this picture, there are lots of inclusions and very few of them are known to be strict. So the known strict inclusions, I think there are basically two. I didn't spend time on the mathematics that's required to show these strict inclusions. So these are called hierarchy theorems. It's interesting, based on universal Turing machine and diagonalization. But this statement before, and a statement against it, the known strict inclusions, the important ones are, I might be missing something, but non-deterministic logarithmic space is properly contained in P space. That's what we get there, and polynomial time is strictly contained in exponential time. That's the really interesting one, because that's spanning a very long part of the picture. Well, actually, both are spanning sort of equally big, but this is the really interesting one because there's such a big gap between polynomial time and exponential time in terms of this picture and the polynomial time. Well, this is sort of efficiently computable. Let's put a efficient. And lastly, there's this red inclusion here. So it's a tricky question, but does anyone know why this is red? So maybe I should just say, of course, both of the above imply P is not equal to, oh no, the second one implies P is not equal to anything. So does anyone see why this one has a different status? So this depends on an assumption. So the very notion of computational zero knowledge proof, for it to be interesting, relied on us having one-way permutations. Well, actually, to show that three coloring has a computational zero knowledge proof, you can get away with just a one-way function, but you need something there to show that three coloring has a computational zero knowledge proof. So the inclusion containing computational zero knowledge proof. Okay. Depends on the existence of a one-way function. So we use a stronger assumption, which is a one-way permutation. In order to do this bit connector, the sealed envelopes. And that's it. I mean, this is essentially a picture of the whole course. It's a lot of complexity classes. I mean, I don't know what your impression is, but there are lots and lots of different complexity classes. You feel you'd like life to be simple with a few basic divisions, but the more you look into things, the more distinctions you see. But it really is a powerful way of looking at the world. So a lot of mathematical problems, it's very actually illuminating to classify where they lie in these complexity theoretic terms. And once again, as I did at the start of the course, I recommend Annie Victorson's book. But if I'd been prepared, I would have remembered the title, but I don't remember the title. But the book that I mentioned in the first lecture, and I think it's linked on the course webpage, I recommend that book as a way of taking this perspective of splitting the world into complexity classes and understanding the relationship of complexity classes from each other, and using that as a lens with which to look at mathematics as a whole and science more generally. Okay, so that's the end of the lecture part, and I'm going to stop the recording now. And I hope the recording has worked out today.